think I heard, there you go, it's recording. So as I stated before, I'm going to talk about exploratory and confirmatory factor analysis and show you how to do it in R. Specifically, what I wanted to talk about were the basics of exploratory common factor analysis. So what it is, why we should use it, the importance of variance and the different types of variance in factor analysis. And I also want to distinguish common factor analysis from principal components analysis. So a lot of folks use these terms interchangeably. I'm sure you've heard it in the literature, people referring to PCA as factor analysis and vice versa. There's actually some fundamental differences between principal components analysis and factor analysis. So I want to make sure we understand the difference between those two. I want to talk about the steps needed to carry out an exploratory factor analysis. So I think Aditi did a really great job of outlining the steps. So I just want to take those steps and then show you the code that we can use to implement those steps and carry out a factor analysis. I want to talk a little bit about confirmatory factor analysis. Not going to spend too much time on that. And then finally, I want to show you guys how to visualize factor analysis results and also how we can report factor analysis. So that's on the agenda for today. I'm going to skip that. So what exactly is factor analysis? So to highlight this, I have a very simple example. So let's say we have 6 items in a scale and I administer the scale to all of you in here. We have one item that references sleep disturbances. So do you have insomnia, hypersomnia? One question that looks at suicidal ideation. One question that looks at anhedonia. Another question that looks at racing thoughts and constant worrying and also nausea. So looking at these items here, are there any items that kind of stick out to you that might group together or might be correlated with each other? Just looking at these 6 items.
Maybe like racing thoughts and constant worrying.
Yeah, I think that those would be related to each other. Anything else you think kind of group together?
Suicidal ideation and dementia.
Yeah, so I think that those would group together, right? So what factor analysis does, or kind of in a nutshell, what factor analysis is doing is looking at the relationship between all these items. So the interrelationship between all these items and see which ones hang together or group together, right? So if you're familiar with the symptomology of, depression or anxiety, then what we could probably say is that the first 3 items represent depression, and then the last 3 items represent anxiety. But it might be the case where some of these items cross-load or load highly on both of these factors, right? So one item might load highly on depression, but also on anxiety as well. So for example, sleep disturbances. So we might have hypersomnia in depression, but we might have insomnia with anxiety. And factor analysis assesses this more formally by testing these interrelationships. And in factor analysis, items are allowed to load on all the factors. And the hard part is the interpretation part, and that's where we come in. We have to interpret this in some type of reasonable manner. So I want to highlight today the steps that we can carry out to kind of interpret this in some type of reasonable manner. So you might be asking yourself, why do we want to conduct a factor analysis? And there's a couple reasons why. The first reason is that it allows us to simplify our data structure. So I don't know if you guys have ever had this experience where you're working on, a particular data analysis data set, and you just have so many variables and so many items. You have no idea how they're related and don't know what to do with them. I've been in that boat before. So what factor analysis allows you to do is take all of those items, all of those variables, and winnow them down to a smaller set of representative variables. So in our case, we had 6 variables here, right? And what we have done is we've kind of reduced these to 2 factors or 2 components, a depression factor and an anxiety factor. So we've taken those 6 items and then shrunk them down to 2. So it makes things more manageable. Another reason why we might want to do a factor analysis is that it can help us identify latent constructs. So we might not know how these items group together, but when we perform a factor analysis, it'll tell us which items group together, and then we can make sense of maybe a common underlying factor that represents these items. And another reason why we might want to do factor analysis is that it can confirm an underlying construct. So are these 2 factors, the depression and anxiety factors, are those representative of our data set? Or are there more factors that underlie our data? So we can perform factor analysis or confirmatory factor analysis, and that can tell us if these two factors are a good representation of our data, our structure. So those are the two reasons why we might want to do factor analysis. So in factor analysis, variance is king. So when we take items or variables and enter them into a factor analysis, there's multiple sources of variance that are taken into account. So an item has common variance. This is sometimes called communality, or you might see h squared. This is the proportion of each variable's or item's variance that can be explained by the other factors. Or stated a different way, is how much an item is related to all the other items in the analysis. An item also has unique variance that's specific to that variable or item. And then there's random measurement error, so unexplained variance associated with that particular item. When we're talking about common factor analysis, we're going to focus on this common variance here. So in common factor analysis, we have this total variance, which equals 1, and we partition that into common variance and unique variance. And common factor analysis is associated with this common variance, this overlap in variance between the items. So when we talk about common factor analysis, there's a focus on the communality between those variables. So the main goal of common factor analysis is to simplify our data, and it does that by trying to explain the maximum amount of common variance using the smallest number of constructs or factors. So if we take these circles here as just overall variance, the common variance is the overlap between those variables here. So what we're interested in when we talk about common factor analysis is this overlap here between all of those variables, the shared variance between those items or variables. That's what common factor analysis is interested in. And you might be wondering, how do we calculate the communality between our variables? And very simply, what we do is we just perform a multiple regression analysis and calculate their multiple R squared. So the idea is that each item in our factor analysis, we treat as a DV, and we regress all the other items onto that DV, and then we extract the R squared from that analysis. And we do that for each item in our data set. So this is kind of a visualization of what I'm talking about here. So if we take item 1 and we have that as our DV, we can regress items 2 through 10 onto that DV. And essentially what we're looking for is the R squared, which is the shared variance of that item with the other items. So this black circle here is our DV variance, and then the yellow circles here are the variance for the other items. And what we're interested in is where there's this overlap here. That's what we're interested in. So for item 1, we can get an R squared. Then for item 2, we can also get an R squared. And then for item 3 and item 4 and item 5 and so forth and so on. This is our communality, or the variance that's shared amongst the variables. So that's when we talk about communality, this is essentially how we're getting that communality or that shared variance between the items. So now I want to differentiate common factor analysis from PCA, or principal components analysis. So common factor analysis is based on the communality or shared variance. Principal components analysis is based on the total variance. So as I stated before, the total variance is equal to 1. That's essentially what we're analyzing in a principal components analysis. It doesn't partition the variance into common or unique. It just throws all the variance into the analysis. So that's the main difference between a principal components analysis and a common factor analysis. The goals between the two are same, right? To find the fewest components that explain the maximum amount of variance or the most variance. But there's some slight fundamental differences between the two, and it has to deal with how the variance is partitioned. So you might be asking yourself, when should I use a principal components analysis? When should I use a factor analysis? So here's some rules of thumb here. So you conduct a factor analysis if you're interested in testing some type of theoretical model or construct, right? You want to extract latent factors from your data, run a factor analysis. If your goal is to just reduce your data to the smallest number of components that explain the maximum amount of variance, then run a principal components analysis. So again, if you just want to reduce your data, run PCA. If you're interested in some theoretical constructs or testing models and latent constructs, run a factor analysis. Yeah, Ham?
What can you use PCA for identifying latent factors?
So it has to do with how the variance is partitioned. So in PCA, we're taking the total variance. We're not differentiating between common variance and unique variance, right? In principal components analysis, we care about the total variance. In common factor analysis, we only care about the shared variance, right? So that lends itself better to testing these theoretical constructs, these latent factors. In general, in practice, both will probably give you the same results. But again, it's about how the variance is partitioned between the two. That's important. In factor analysis, we just care about the shared variance, which lends itself to identifying latent constructs that explain the items or the variables.
But even PCA is giving you the first component is basically the component that explains
The most
of the
variance, yeah.
across all the factors.
Just that factor. So the first factor that's usually extracted is the one that usually typically explains the most variance. And then the second one would explain the least variance and so forth and so on. But again, it's just the fundamental differences about when you'd want to perform one versus the other. And it has to do with how the variance is partitioned, essentially. But again, in practice, both probably would return reasonable results. Again, there's just a focus on the shared variance in factor analysis that lends itself to testing latent constructs. Whereas in PCA, we're interested in extracting the components that have the most variance, but that are independent from one another. Make sense? No?
So factor analysis is not extracting independent components.
So PCA is extracting independent components. In factor analysis, we usually let those factors correlate with one another, right, if they want to. So that's one of the differences, right? When we perform rotation, we might let them correlate with one another. But in general, PCA is independent components. Yeah.
So why do we want latent factors to correlate with each other? What's the virtue of that?
Because in the real world, things correlate with one another. I mean, independence makes things a lot simpler and easier, right? So you might want that, but you can let them correlate.
Extreme end, why don't we just take all the items from a survey and treat them as separate things, right?
Why would you want to treat them as separate things if you're trying to figure out a latent kind of underlying construct?
To figure out a latent variable, shouldn't we find them as independent as possible ones?
I mean, I think that makes it easier, but I think that in real world, it's not that clear and simple, right? I agree with you that independence between the factors is ideal, but that's sometimes just not how it works, right?
Also, the problem is like usually you get uninterpretable.
Yeah. But, yeah. All right. So before we jump into actually analyzing some data and conducting a factor analysis, there's two terms that we should define. One is eigenvalues and the other one is eigenvectors. And this is a very simplified representation of these things. There's some really complicated matrix algebra that underlies all of this, but we're not going to get into that. But generally speaking, eigenvalues represents the total amount of variance that can be explained by a given factor. So this represents factor importance. The higher the eigenvalue, the more variance that it explains. Eigenvectors represent a weight for each eigenvalue, and eigenvectors are important because we can take that eigenvector, which is a numerical value, and we can times that by the square root of the eigenvalue, and we get a thing called factor loadings. And this is what we interpret in a factor analysis. And as Aditi already stated, a factor loading basically is just the correlation between that item and the factor, the unique relationship between the item and the factor, if we're talking about the pattern matrix. All right, so now let's go ahead and talk about the steps that are needed to conduct an exploratory factor analysis. So ideally here, we want to extract factors and we want to figure out what items load on that factor. So there's 5 steps that we need to undertake. The first step is to decide if we can run a factor analysis on our data. So is it suitable? The second step is to decide the number of factors we want to extract. The third step is factor extraction, so extracting the loadings. The fourth step is factor rotation, which helps make our factors more interpretable. And then in the last step, the fun part, we get to name our factors in some type of meaningful manner, or meaningful way. So to highlight these steps, we're going to use data from 2,800 participants. We have a very large sample size, and each participant answered 25 self-report items, Likert scale items, from the Big 5 inventory. So the Big Five inventory, for those that don't know, is a personality theory that states that there's kind of 5 major facets or dimensions of personality. One facet is conscientiousness, the other is agreeableness, there's emotional stability, openness to experience, and extroversion. And each item in the inventory represents one of these categories. So let's go ahead and take a look at the actual items that people look at. I already did that. So here's just an example of some of the items that people answered. So they're labeled alphanumerically related to the dimension, which makes our lives a lot easier. So A1 is agreeableness, so am indifferent to feelings to others. We have conscientiousness question, so do things in a half-manner way or halfway manner. Extroversion, I know how to captivate people. Neuroticism, gets angry easily. And then we have openness, so I'm full of ideas. So this is just an example of some of the questions that folks answered in the survey. So let's go ahead and load in the data set. So what I'm doing here in each line is I'm loading in the data set and I'm extracting the 2nd to the 25th column. And the reason why I'm doing that is I just want the items from the inventory. I don't want any extraneous columns in the data set. So I believe there's things like high school or education and gender and stuff like that. We don't want to put that into the factor analysis. And then I'm also deleting missing data here. So let's go ahead and take a look at the actual data set, see what it looks like. So hopefully you'll notice here that each item is a column and each participant is a row. So when we're performing factor analysis, we want to make sure that our data set is set up this way in the wide format and not the long format here. All right, so as a first step in factor analysis, we want to take a look at the correlation matrix. So we can output the table, but I find that indecipherable. So I much prefer to actually visualize our correlation matrix. So I provided the code to produce this particular correlation matrix, which I actually like, where each of the squares, the size of the squares represent the magnitude of the correlation, and the color represents the direction of the correlation. So looking at the interrelationships between these items here, is there anything that kind of sticks out to you about how the items are related? What items correlate highly with one another here?
Some triangles, but I don't know.
Is it? Yeah, so the neuroticism, what do they correlate highly with?
Other neuroticism.
Yeah, other neuroticism items. Is there any other? So what do the agreeableness items correlate highly with?
Themselves and extroversion.
Yeah, so what I want you guys to kind of see is that the agreeableness items correlate highly with the agreeableness items. The conscientiousness items correlate highly with the conscientiousness items. So again, it seems like there's a high correlation between items that measure the same things. So this would give an indication that these items have some type of common underlying factor. And we know what that factor is. So we know there's an agreeableness factor, we know that there's a conscientiousness factor, an extroversion factor, and a neuroticism factor, right? So the
extroversion ones are like negatively related.
They're negatively related, but they're highly, yeah, so they have a high loading, so. And most of the time, we just look at the actual magnitude, and sometimes we ignore the actual sign of them. But it's possible, too, that some of these are not reverse coded, right? So that could be something that we look into, but yeah. But generally speaking, the magnitude, it seems like the agreeableness and the conscientiousness and extroversion correlate highly with their counterparts here. So I have a note here that, so when we're writing up our results or writing up a factor analysis, we should always include the correlation table. So we can actually perform a factor analysis just based on the correlation matrix. So it's always good to include that in the appendix or in the paper itself. So someone could reproduce your work or do further analysis on that work. All right, so the first step in a factor analysis is to make sure that the data is suitable. And there's a couple tests that we need to perform to ensure that our data is suitable. One test is called the Bartlett's test of sphericity. And this test compares the correlation matrix of our data, so this thing right here, to what's called an identity matrix, where there is no correlations between the variables. So this is an example of an identity matrix where we have ones on the diagonal and then zeros on the off diagonal. This says that there's no relationships between the variables. And we're gonna look at a chi-square statistic, and if it's statistically significant, that means that there are correlations between the variables, and if it's not statistically significant, that means that there's no correlations and that factor analysis is not suitable. So that's the first test. The second test we're gonna perform is the Kaiser-Meyer-Oken test, or the KMO test. And this test looks at the sum of the correlations squared divided by the sum of the correlations squared plus the sum of the partial correlations squared. Does anyone remember what a partial correlation represents? Kind of think back to when you learned correlations. So partial correlations represent the unique relationship between two variables, partailing out all the other variables. So in this context, what the KMO is trying to assess is if the partial correlations are small, because if they're small, that means that the variables share a common factor and that the unique variance is pretty low, and that's what we want. We want the sum of the partial correlations to be smaller than the sum of the correlations, because that would indicate that the variables have a lot of shared variance with the other variables. So that's what we're looking for here. And the KMO value ranges from between 0 to 1. And we want the KMO value to be pretty high. And there is some debate as to what that KMO value should be. Here I'm stating that it should be 0.7 or greater. Some folks will say 0.6 or greater. So if your KMO is 0.6 or greater, that means that you can perform your factor analysis, that there is some shared variance in your data set. We wouldn't want to perform this, again, if there's just unique relationships and there's no shared variance here. So luckily, Easy Stats has us covered because they have a function called check factor structure where we just throw in our data and it will output the Bartlett's test, it will output the KMO, and it will output this thing called sampling adequacy. So when we put in our data set, it'll return the Bartlett's test and we see that it is statistically significant, so that's good. We get our KMO test and the KMO is 0.85. So that's also good, right? We want our KMO to be greater than 0.6, 0.7, so that's awesome. If our KMO was less than 0.6 or 0.7, what we could do is we could look at the individual KMO scores or the sampling adequacy of each item, because that's also calculated. And generally speaking, what we'd want to do is we would delete items that have an MSA of less than 0.5. And then we can rerun this and see if that improves our KMO value. And then we could proceed on with our factor analysis. But everything looks good here, so we can proceed on with our factor analysis. So as Aditi and Brooke talked about, there are several assumptions with the factor analysis. So we shouldn't have any outliers in our data. We should have a fairly large sample. So this is dependent on how many variables or items you have in your data set. But generally speaking, probably greater than 100 participants would be nice. The data should be normal. There should be no missingness and there should be no multicollinearity. And I didn't put it on here, but when you're conducting a factor analysis, you should have continuous data. So it should be on the interval or ratio scale. And it's common to use ordinal scale items in a factor analysis. So like Likert items like we're doing here, or Aditi did with her data set here. But there's some debate. You should not be putting in categorical variables into your factor analysis. There is a special type of factor analysis called correspondence analysis. So if you want to do a factor analysis on categorical data, there's a separate analysis that you should do. You should not be putting in categorical data into this factor analysis. All right, so what I have here is a function from EasyStats called check outliers. So folks in Psych 503 should be familiar with this. This checks the outliers in our data set. And then I provide some code here where we can delete the outliers. So we shouldn't have outliers in our data set. This detects about 82 of those, but we have a huge sample size here. So it shouldn't matter too much, but we're going to remove those from the data set. And that's what this code reflects here. So another issue that we need to address is multicollinearity. So we want our variables to be correlated with each other. However, we don't want them to be perfectly correlated with each other or to have really high correlations with each other. And one way that we can assess this is by looking at the determinant of our correlation matrix. So underlying factor analysis, underlying regression is matrix algebra. And any type of matrix, a square matrix, should have a determinant. And if that determinant is super small, close to 0 or is 0, then that indicates a problem with multicollinearity. So we want to check that with our data to make sure we don't have any multicollinearity issues. So what I'm highlighting here is how to extract the correlation matrix, so using the core function, and then we can get the determinant of the correlation matrix using the DET function here. And we see that the determinant is 0.005, which is greater than this value here. So we can say that we don't have multicollinearity in our data, which is good, which is what we want. All right, so now that we've determined that our data is suitable for factor analysis and we got rid of the outliers and we checked for multicollinearity, now we can extract the number of factors, or we can extract factors from our data. And there's several different ways that we could do this. So there's several different ways we can determine the number of factors in our data. One way is based on theory. So in our example, we're using data from the big five. So it would be perfectly reasonable to say there's 5 factors in our data set. So we could set the number of factors we want to extract to 5. Sometimes we don't have theory guiding us. So there's some other methods that we could use. One method is the eigenvalues greater than 1 that Aditi talked about. This is called the Kaiser criterion. So remember that eigenvalues represents the proportion of variance explained by that factor, with higher eigenvalues indicating greater amounts of variance. So we would take all of the factors that have eigenvalues greater than 1. This is not really used anymore, but it's still a method. The other one is the cumulative percent variance extracted. So essentially what we're doing here is we're tallying up all the factors that have about 75% cumulative variance, right? So that's how many factors we would take if they total up to 75% of the variance. Another method is to use what's called a scree plot, which I have depicted here. So a scree plot is usually visualized with the dimensions or factors or components on the x-axis. And then we have eigenvalues on the y-axis, which is the percent of explained variance. And these bar graphs are not usually depicted, but I particularly like this visualization. Usually what we'll see are these little kind of line graphs here. And what we want to do with our scree plot is we want to detect where the elbow is or the inflection point of this figure. So this is the point where the variance starts to level off and there's really no changes in the variance. So looking at this scree plot here, where do you think the elbow is? Where does the variance seem to level off the most? Anybody want to take a guess?
6.
6 is pretty reasonable, right? I feel like that might be where it levels off the most, right? So in this case, what we would do is we would take all the factors above this. So you said the inflection point was 6, so we're going to take 5 factors from here. However, this is a very subjective endeavor, and it's not really reliable. So Chris, you say 6. Someone might say, I think it's 5. That seems like a good elbow for this scree plot. So it's not really reliable. So what can we use that's more objective and reliable? And Aditi talked about this. It's called parallel analysis. So this is kind of one of the most preferred methods in trying to decide how many factors we should extract. And parallel analysis is dependent on Monte Carlo sampling from a distribution. So the idea behind parallel analysis is that we basically pull from a distribution that has the same number of variables and the same sample size as our actual data, and then we calculate eigenvalues from that random data set. So these are meaningless eigenvalues. So the idea here is to compare these meaningless eigenvalues to the eigenvalues from our data. And what we would want is to take the eigenvalues that are greater than the eigenvalues that were extracted from this random generating process. So that's the basic idea behind parallel analysis. And I'm showing the code how we can conduct the parallel analysis in R using the psych package. So today we're primarily going to be using functions from the psych package, but there's other packages out there that exist, but I like the psych package. And there's a function called FA parallel. We feed in our data, and there's some other arguments that we have to specify too. Here we're specifying that we're going to do a factor analysis. We could also specify a principal components analysis as well. And what I like about this is that it automatically produces this figure here. So we have our parallel analysis here, and it's kind of hard to see, but there's these red dotted lines here. This represents the eigenvalues from our parallel analysis. And what we want to do is we want to take all the factors above that line. And what's good about this function is that it tells us how many we should extract. So here it says 6. So Chris was right. We should extract 6 factors here. So that's what the parallel analysis states. However, we shouldn't be using just one method to determine this. So this says 6. I might have said 5 here. So there might have been some ambiguity about the number of factors to extract. So my preferred method, or the one that I like, is a consensus method or an agreement method. So this looks at a whole bunch of different methods and calculates the percent agreement. And luckily, EasyStats has a function that does this for us in one line of code. So there's this n factors function from EasyStats where you put in the data and it just performs this agreement or consensus method. And what this is telling us is, so we have number of factors on the x-axis, and then we have percent agreement out of 19 methods. So it has 19 methods that it performs this on with our data. And what we want to do is go with the number of factors that has the highest percent agreement. So here it's 5. So I think 5 is a good number to extract, 5 factors. So that's what we're going to go with. Oh man, I think that the procedure that Aditi followed, where you're comparing like different numbers of factors and see which is more interpretable, would be fine in that case. So you might fit a factor analysis with 5, and then you might fit a factor analysis with a 4 and see which one is more interpretable. That's probably how I would go about that. Yeah, so I'm presenting this as clear cut, but it's not clear cut, or it can be really messy. All right. So we've decided on extracting 5 factors from our data. That's what the agreement method suggests. So now we can actually extract the factor loadings from our data. And there's a whole bunch of different methods that we can use to do this. I'm going to highlight one known as principal access factoring, but there's methods like, maximum likelihood and a whole bunch of others. But I thought that I would talk about principal access factoring because it's kind of traditional and it's mostly the default for most factor analyses. So the basic idea behind principal access factoring is that we just take a correlation matrix, like I have depicted here, and we start off with the communalities, which is just the multiple R squared for each item. And we perform what's called an eigen decomposition process, which I'm not going to go over, but basically we're just calculating the eigenvalues and eigenvectors. And then what we're going to do is we're going to take out that variance and then we're going to rerun it again with different communalities on the vertical. And then we're going to do it again and again and again, dependent on how many factors we're extracting. And each time we're going to calculate the eigenvalues and eigenvectors for our data set. So this is in a nutshell what principal access factoring is doing. This is how we get our factor loadings. So now let's go ahead and actually run our factor analysis. So as I stated before, we're going to be using the psych package, and there's a function called FA that will perform factor analysis. And what we need to do is we need to input our data, the number of factors we want to extract. Here we're going to set rotation to none. We're going to do rotation in a bit, and then we're going to set our method to PA, which stands for principal access factoring. And when we look at the output from our object, we see a whole bunch of stuff here. What I'm going to focus on is the factor loading matrix and the variance matrix here. And I've cleaned this up by using model parameters from EasyStats. The code is in the Corridor QMD document if you're interested in how to produce that, maybe for lab on Wednesday. But essentially what I wanted to do is highlight some of the components from the correlation matrix, or what's sometimes called the pattern matrix. So that's what's produced by default with the PSY504-FA package. And each of these values represent a correlation between that item and the factor. So we can see for A3, the correlation is 0.54, so that's how it correlates with that first factor. And ideally, we want high loadings, right? Because that means that that particular item correlates highly with that factor. And we would want low loadings if it doesn't correlate with that factor.
It's a negative correlation.
So it's very possible it could be negative, and that could be because you didn't reverse code your items. But usually we look at the magnitude. That's the important part, because a negative loaded items means that it could load on that factor highly, but it might be kind of diametrically opposed. So I'm thinking of maybe something like extroversion, introversion type of thing, but it could be. So at the top of the table, we have names. So this does not label the factors intuitively. So you get a factor called PA1, PA2, PA3. Don't put this as your factor names when you're writing a paper. This is not interpretable. This basically just reflects the fitting method that are used to fit the factor analysis. But it just produces names for you. But this represents the first factor, this represents the second factor, and so forth and so on. We also have complexity scores. This is the number of factor an item loads on. Here we would want the complexity to be 1. We only want items to load on 1 factor, but in the real world, that's not likely. And then we have uniqueness values, which is 1 minus the communality. And here we also want these numbers to be low, because we want high communality values and low uniqueness values, right? We want a lot of shared variance here. And for some reason, the EasyStats function, when you look at model parameters to get a cleaner version of the tables, doesn't include the communality values. But I'm going to show you a way that we can extract the communality values to put in a table. But for some reason, it doesn't include it. Another important part of the output is the variance accounted for, or variance explained table. Here we have the SS loadings, which is the sum of square loadings, which is basically the eigenvalues for our factors. And remember, the eigenvalues is the proportion of variance explained. So how we can calculate the eigenvalues is basically just taking the correlations for each item in a factor and squaring it, and then just summing down. And then if we do this, we get our eigenvalues for each factor here, where PA1 explains the most variance, PA2 explains the least amount of variance, and so forth and so on. We also have proportion variance and cumulative variance of each factor, and proportion explained and cumulative proportion explained. Before I talked about how we would extract factors, we would look at the cumulative proportion if we wanted to use that as our criteria to determine the number of factors we'd want to use. All right, so what we have here is a visualization of the factor analysis that we just ran here. So looking at this, I know it's kind of hard to see, but you can kind of make out the items and then the factors here. Is there anything that kind of sticks out or jumps out to you guys about this factor analysis we just ran?
Like some of the factors have like more
Yeah.
variables associated
Yep.
with them than others.
Yep. So that's kind of a problem. So we didn't use a rotation method here. We just performed factor analysis. And what happens commonly is that all the items will load really highly on the first factor, and then they're less likely to load on the other factors, which we're seeing here. And there's also an issue of things not loading where they're supposed to know. So the reason why I chose this particular data set is we know that there's agreeableness items that represents an agreeableness factor. There's an eroticism component. And what we see here is that some of the items are cross-loading, or like some of the agreeableness and conscientious items are loading on the first factor. And then there's less items loaded on the subsequent factors here. So that's problematic. So one way that we can make this more interpretable for us is by using rotation. And the purpose of rotation is just to make our factor solution more interpretable. It doesn't do anything with the relationships among the variables or the variance explained. What rotation does is it makes the higher loadings higher and the lower loadings lower. And this is done to achieve what's called simple structure in factor analysis parlance. And what simple structure is essentially that for each factor, or for the factor analysis solution in general, each row contains at least one zero loading, right? So an item loads only on one factor highly and loads lowly on all the other factors. For each column, so for each factor, there's at least as many zeros as there are columns. For any pair of factors, there are some variables with zero loadings and large loadings on the other factor. For any pair of factors, there's a sizable portion of zero loadings. And for any pair of factors, there's only a small number of large loadings. So when you hear about simple structure, that's what this represents here. And one way that we can achieve simple structure is by engaging or applying a method called rotation. And there's different types of rotation methods. There's orthogonal rotation. And essentially here, we're just rotating the factor solution 90 degrees. So the factors are independent from one another. There is a correlated rotation method, sometimes called oblique rotation. And this allows the factors to correlate. So essentially here, and I'll show you an example of this, but when we rotate the factor solution or the factor space, it's allowed to rotate less than 90 degrees so they can be correlated with one another. And to make this super simple, I don't know which rotation method to use, always use an oblique rotation. That's what you should be using. There should be no, should I use orthogonal, should I use oblique? Just use the oblique rotation. And the reason why is because one, things in the real world are correlated with one another, so let them be correlated. But the second reason is if your factors are indeed not correlated with one another, then the oblique rotation will not make them correlated. So it doesn't make sense to run an orthogonal rotation. We should just run an oblique rotation.
Is orthogonal rotation the same as PCA?
So you can, so with PCA, you could perform different types of rotations. So you can make them orthogonal or you can make them oblique if you wanted to.
PCA by definition gives you orthogonal factors, right?
So the independent components are independent. So they should be independent, but you could allow them to be correlated if you wanted to. But they should be independent, right, if you rotate them.
So if you rotate the result of factor analysis orthogonally, does that give you the same result as PCA? Or still maybe different?
They might be different, but yeah, they might be different. But again, it's different. The partitioning of the variance is different between the two. So here, what I'm talking about primarily is just common factor analysis and not PCA. So to highlight this example, I want to use a really simple example. And what we're going to do is we're going to look at just two factors. And what I've done is I've plotted them in factor space, where we have on the horizontal axis factor 1 and on the vertical axis factor 2. And these diamonds just represent the loadings for each factor here. And if we look at the loadings, which represent the correlation between that item and the factor, what we see here is that the first 4 items load pretty highly on factor 1 and pretty low on factor 2. So that's good. But let's look at items 5 through 8 here. So item 5 here loads moderately on both factors, so there's some ambiguity there. Item 6 seems to load a little bit more highly on factor 2 than factor 1, but it's not clear. Same thing with the 7th item and the same thing with the 8th item here, right? So there's some ambiguity here. So what we can do is we can rotate the solution. And essentially when I say rotation, we're taking the axis and factor space and just rotating it. So with an orthogonal rotation, we're just rotating this at 90 degrees. And with oblique rotation, we're rotating it less than 90 degrees. And this serves the purpose of making our factor loadings more interpretable. So magnifying those high loadings and then minimizing the low loadings. So once we perform this rotation method, again, we see that the first 4 items load highly on factor 1 and lowly on factor 2. But now the items 5 through 8, now there's a clear distinction between the factors. So we see here that item 5 now loads more highly on factor 2. It loads more highly on Y6 loads more highly on factor 2. Y7 loads more highly on factor 2, and then Y8 loads more highly on factor 2. And we see that the factors loadings on factor 1 for those items have been minimized here. So again, this serves to make our interpretation more interpretable and more understandable. And the same thing happens with oblique rotation as well. We see the same general pattern here, where the first 4 items load highly on factor 1, and then the last 4 items load highly on factor 2. So that's the main purpose of rotation. And we can set rotation in our factor analysis. So essentially, once you decide on the number of factors you want to extract, when you perform your factor analysis and you select a method for extraction, like principal axis factoring, just set a rotation method. This should not be none. So you should choose a rotation method. If you wanted to use an orthogonal rotation method, you could use the Varimax. There's a whole bunch of different methods you could use. These are kind of widely used. So if you want to do an orthogonal rotation, use Varimax. If you want to use a oblique rotation, use Oblomin. Or you can use Promax like Aditi did in her example here. That's also fairly common. So we can rerun our factor analysis using the rotation Oblomin. And now we have our factor solution now. And hopefully this looks a little bit better to you guys than the last one. So not all of the items are loading highly on the first factor. And now we see that the neuroticisms items seem to load on one factor, the extroversion items seem to load on one factor, the conscientiousness items, and so forth and so on. There's some weirdness going on here where this openness item is loading on extroversion, but we could talk about that if you want. But for the most part, it seems to be pretty interpretable. So in addition to rotation, what we also do to make things more interpretable is we delete correlations that are less than 0.32. And the reason for this is that if we squared this correlation, it only accounts for 10% of the variance. So what we usually do is we just take the items that don't have a correlation of 0.32 and we just remove them from the factor. And you can do this manually, right, by setting a code, by looking at the table and just getting rid of those. In easy stats, we can use model parameters, and they have a threshold function, or a threshold argument, excuse me. And you can set this to 0.32. And this will remove all of the items that are not, that don't have a correlation of 0.32 or higher. So that can make things more interpretable, but if that still doesn't make things interpretable, what we can do is we can set the threshold to max. And that will make sure that we have a simple structure where only items with high loadings are loading on a particular factor. So once we do this, we can start to name our factors or interpret them. So as I stated before, PA1, PA2 are not very intuitive factor names, so we should give these intuitive names or labels. And this is an art form, really, and it's highly subjective. But one kind of suggestion is to look at the items and see which ones load highest on that factor and use that to help you name the factors. So let's go ahead and do that with our data. So here I've set the threshold to max. And what you'll see here is that all the items are just loading on one factor and one factor alone. As I said, there's some weirdness here with openness items loading on extroversion, but we're just going to forget that. Each item loads on one factor only. So that's essentially what we want here. And luckily, these items are named intuitively already for us. So we know that the first 5 items here represent neuroticism. So we would name that factor neuroticism. The second factor seems to have the extroversion items loading highly on them. And we can see that the highest loaded items are extroversion items. So that factor would be extroversion. And then the third factor could be something like openness and so forth and so on. So that's how we would interpret or name these variables. So what makes a good factor? So there's several things that make a good factor. One is that it makes sense. So we want items that measure the same thing loading on a factor. We don't want items that measure different things loading on a factor. That's problematic. We want to make it easy to interpret. So we need to make sure we have a simple structure for our factor solution. So this means that our factors have high loadings and really low loadings and really few moderately sized loadings. We don't want cross loadings where items are loading on multiple factors. So what we can do is we can keep items that are greater than 0.32, so have a higher correlation than 0.32, or we can just look at the max loadings. If we still have cross loadings after we, use the correlations greater than 0.32, what we could do is we could look at the communality of each item that cross loads, and then maybe get rid of that item if it has a low communality, so a load share variance. You typically less than 0.5 is used. So we could look at the communalities and determine if we need to get rid of that particular item if it cross loads. And then also you should have 3 items per factor. That's kind of the general rule of thumb, and this has to do with structural equation modeling and identification of the model. So these are just some things that make a factor good. So one cool thing that we can do with factor analysis is we can extract what are called factor scores. And factor scores are scores for each participant that represents their standing on that factor. And what we could do is we could use these factor scores and we can put them into a regression analysis. And there's lots of different ways that we can calculate these regression or factor scores. One way is through regression. And I kind of just highlight here how we can go about calculating those. That's not really important right now. But what I wanted to do was kind of exemplify one way that I've used factor scores in my research, because I just think that they're really cool. So colleagues and myself, we performed a factor analysis. And you can tell the difference between a PCA and a factor analysis by what's on the diagonal here. So because ones are on the diagonal, we performed PCA, principal components analysis here. But what we wanted to do is we wanted to take all of these language measures, like the pyramids and palm trees test, lexical decision, the Philadelphia naming task. We wanted to take all of these tasks that we had, and we wanted to winnow them down into a select number of language features. And we were able to get some really nice, clean results. So we were able to get a factor that represented the semantics. We were able to get a factor that represented speech production and speech recognition. So we got these really nice, clean factors. And what we did is we submitted these to a regression analysis, and we used them as predictors to predict language damage or brain damage in the brain to particular white matter tracts. So we looked at white matter disconnection in the inferior frontal gyrus, and we looked to see if semantic impairments predicted damage to that area in the brain. So this just gives an idea of how we can use these things in our research, right? So the exploratory part is important where we're extracting these factors, but we can actually use them as predictors to test things that we're interested in, which I think are really cool. All right, so now I want to talk a little bit about visualization. So there's lots of different ways that we can visualize a factor analysis. I really like this way. This is what I stole from my postdoc advisor because I really like the visualization. So I've used this in a couple papers. But essentially what we're doing here is we're visualizing the loading strength on the x-axis by these horizontal bars that differ in transparency. We have items on the y-axis, and then we have faceted factors here. And I like this particular visualization. So this is the absolute loadings, right? We're not using negative loadings here just to conserve white space. But we can kind of see which items load highest on each factor, right? So the lower the loadings, the more transparent those bars are. So the ones that have the highest loadings kind of pop out more. And we can kind of see nicely that on factor 1, we have the extroversion items. Factor 2, we have the neuroticism items. Factor 3, we have the extroversion items, and so forth and so on. So I provided the code here to recreate or reproduce this. So if you want to use this figure for Wednesday's lab, you have the code to do that here. But I like this particular visualization. We can also represent this factor analysis in a table. And I found this really cool function called FA table. So I have the way that you can get the R code to produce this table here. And why I like it is because it's one line of code. And it produces something that looks like this, where you can just put it into your paper. So obviously we have to do some cleaning up So factor 1, factor 2 is not really meaningful. So we would change these to neuroticism and extroversion and so forth and so on. But it gives you everything that you'd want to report in a paper. So it gives you communality, it gives you uniqueness values and also complexity values. And what I like about this too is that it highlights items that cross-load on that particular factor or cross-loads on multiple factors here. So it'll highlight in red. And as I stated before, we can look at the communality values for items that cross-load, and we can make a decision as to whether we want to maybe remove that item from the analysis. So neuroticism here, the communality seems to be pretty low, but we might keep that. But the other items here like openness, which remember, loaded on an extroversion factor, which is weird, but we might decide to get rid of this because the communality is so low. And then also the extroversion 3 item here also seems to have low communality here. With these cross-loaded items, we might choose to maybe just get rid of them and rerun the analysis. But there's that. All right, so now I want to talk a little bit about confirmatory factor analysis. So EFA tells us how many factors to retain. So here we retain 5 factors. Confirmatory factor analysis, which remember is under the umbrella of structural equation modeling, tells us how closely our data fits our expectations or how closely our data fits that model. So is a 5-factor solution really the best model for our data? So we can test this with confirmatory factor analysis. And as a caution here, never do a confirmatory factor analysis on the data you performed your exploratory analysis on. So as Aditi mentioned, she performed multiple experiments or multiple follow-ups looking at a confirmatory factor analysis on a new set of data, correct? Yeah. So never use the data that you performed your exploratory analysis on. So there's a way that we can do this, and it's not used in the literature that I've seen, but I think it's a useful approach, and that's a machine learning approach, where basically what we do is we take all of our data and we partition it into a training and test set. So here we can use a easy stats function called data partition, and we put in our data, and then we can specify the training set and then also the test set. Here we're doing a 70-30 split, so 70 training and then 30 test. So this allows us to do this super easy, super simple. And here what we can do is we can have our training data set where we perform our exploratory factor analysis and then use the test set to do our confirmatory factor analysis, which I think is a really useful method. However, we need to have lots of data here. So that's the one caveat of using this approach. But here we have lots of data. So what we're going to do here is we're going to compare 2 models. So we have our big 5 model, right, that we fit. But there's also another personality theory that's out there that says that we don't have 5 personality facets, we have 6. This is called the hexaco model. So let's just compare these 2 models and see how well they fit the data. So here I'm just rerunning our factor analysis again with 5 factors. And then there's a really useful function called EFA to CFA from EasyStats that will basically give you the Lavon output that you need to perform your CFA. So that's what I have outputted here. This is our 5-factor solution. And then we're going to compare this to a 6-factor solution. And again, we're just outputting the Lavon code that we can use. So we don't have to specify this manually, which I think is nice. And what we're going to do is we're going to use a function from Lavon called CFA. And we're going to fit a CFA to our big 5 and then a CFA to our big 6. And then what we're going to do is we're going to compare these models. So we're going to look at model fit indices, and then we're going to look at a chi-square change. So we're going to look at a likelihood ratio test between the 2 models to see which one is preferred. So what I have highlighted here are the fit indices for our 2 models. So looking at our chi-square statistic and the chi-square p-value, we see that it is statistically significant. Is this a good thing or a bad thing? So both models are statistically significant. Is that a good thing or a bad thing? Got to think back to last week when we talked about fit indices. Anyone remember what the cutoff is for this, for a good model fit? It's bad, correct, yeah. So this is bad. We want this to be non-statistically significant, but because we have so much data, it's always going to be statistically significant. So we usually use other fit indices to test this. So Another fit indice that we use is CFI, and the CFI is 0.78. Does anyone remember what the cutoff is for the CFI? So this is kind of a goodness of fit statistic. So higher is better here, but does anyone remember the actual cutoff score? .9. So close, 0.95. We want this to be as close to 1 as possible. This indicates poor model fit. We have the RMSEA, so I'll spare you guys the trouble. This should be less than 0.08, so less than or equal to 0.08. So it's right on the cusp. So I guess it's okay. And then the SR-MR should also be less than 0.08 or less than or equal to 0.08. And it's right on the cusp of this. Overall, I would say that these two models are not the best, but we're going to go ahead and compare these two models anyways, and we can use the likelihood ratio test to compare them. So that's what I have highlighted here. And we see that the chi-square between the two models is not statistically significant. So what that suggests is that we go with the more parsimonious model here, and that's the big 5, right? So there's more degrees of freedom in that model, so it's more parsimonious. So this is how we would do some model comparisons or model tests in a confirmatory factor analysis framework. All right, so to wrap up, what I wanted to do is talk about what we should include in our paper when we write it up. So here I have just a table of things that you should include, but at the bare minimum, these are the things that we should include in our paper. We should talk about factorability, so we should include our KMO value, we should include the Bartlett's test, and we should include the determinant of our correlation matrix to make sure there's no multicollinearity. We should also talk about the number of components we extracted and justifications for those. So did you use a scree plot? Did you use eigenvalues greater than 1? Did you use a parallel analysis? Or did you use an agreement method? You should list the extraction method you used. So did you use principal access factoring? Did you use maximum likelihood? The type of rotation you used, so was it orthogonal or oblique? You should include the factor loadings. So you should place those in a table or a figure. And then lastly, you should also have your correlation matrix. So you should put that in the appendix or in the body of the table if you can, depending on how big your correlation matrix is. So these are the kind of the minimum things that you should include in your write-up. And I have some sample write-ups here. So you, when you have time, you can look at those if you'd like. So to kind of wrap up everything, what is factor analysis? It's a method where we can extract the most variance from our data, whether it's common variance or total variance in the smallest number of factors. When should you use factor analysis? When you have lots of variables or lots of items. You should use it when your measures are correlated or you're interested in testing some type of latent construct. Why should you use factor analysis? It helps simplify the data. And it also allows us to identify underlying constructs of our data, but also allows us to test underlying constructs as well. So do we have a big 5 or do we have a big 6 in our data? And we can use structural equation model and confirmatory factor analysis to test these things, which makes it very useful. All right, so some class announcements to wrap up the class. So Wednesday is the last lab of the semester. I would like all of you guys to be here. I am planning to bring some desserts. Are there any type of dietary restrictions that I should know about? I was going to keep it pretty simple. What are your dietary restrictions?
I'm vegan,
Okay.
but I also don't mind if you don't bring vegan stuff.
Oh, no, I could bring vegan stuff for sure. Same thing, Ham?
No.
Okay. Any other dietary restrictions? So yeah, so I'll try to bring an assortment. So usually I'll like go to, yeah, it's delicious one. So I'm thinking munchkins from Dunkin' Donuts, but then also I go to Whole Foods because they have a vegan selection and get some of those pastries. So that's kind of what I'm gonna get to bring to class. So come to class just for that. But the lab on Wednesday is going to have you do an exploratory factor analysis on some data, and then also a confirmatory factor analysis. So we're going to combine structural equation modeling from last week and factor analysis from this week. Just as an announcement, all lab revisions are going to be due at the end of reading period. So this requires you to comment on my comments from your labs and then resubmit them. So if you haven't done that, try to get those into me by the end of reading period.
What's the date for the end of reading period?
That's Sunday. I don't, does anyone have the,
Well, it's technically Tuesday the 7th, I was just Googling it. It's like a week.
oh, is it, it's the 7th? Yeah, so the end of reading period. So if it's on the 7th or on the 5th of May, whatever.
Oh, okay.
So the 7th or 5th of May, just try to get the comments to me and resubmit the labs. I think most of you have been keeping up with that, so it shouldn't be too much extra. And then lastly, the blog posts are going to be due by May 13th. Grades are due on the 20th, so I want to have at least a week to provide feedback and take a look at your blog posts, and just really soak them all in. So try to get those to me by May 13th. Obviously, if there's some conflicts or you're not going to be able to do that, just email me. You guys know by now that I'm pretty flexible and lenient, so if that's going to be an issue, just let me know. So that is all that I have. Does anyone have any questions, comments? Yeah.
Blog post doesn't have to be one of the topics in the weeks, right? You could reach about any package, statistic package.
Yeah, so I'm allowing, extreme flexibility on this. So if you want to cover another analysis technique, you could do that. If you want to cover a package and kind of run some data on it, you can do that as well. Just, I want you to explain something for a general audience that I can then pass along to other folks if they're interested in learning about a topic. But it should be for the lay audience. But yeah, no, the topics it's open. So do whatever you feel comfortable with. So all right, you guys are free to go if you don't have any questions. You can stick around and ask me questions if you want to. But I will see you guys on Wednesday.